Well, thank you very much for inviting me to give a talk here. I'm going to speak about the motion of particles, or actually ultra-cold atoms in quasi-periodic potentials. So this is the joint work with Ivan Alexeyevich Dynnikov from Steklov Mathematical Institute and Moscow State University. So first of all, I'm sorry. First of all, we are going to consider quasi-periodic potentials on the plane, which means that the potential is going to be a restriction of a periodic function in the space of higher dimensions under some embedding of two-dimensional plane into the three-dimensional space, four-dimensional space, and so on. The theory of quasi-periodic functions goes back to the studies of Harald Bohr and Besikovich. And here, just to avoid any misunderstanding, we call the quasi-periodic function, as I said, the function given by a restriction of a periodic function of high dimension under some affine embedding of R2 in RD. Well, here we are going to consider some applications of the geometry of quasi-periodic functions, and these applications will be mostly connected with the transport behavior of non-interacting gases in such potential, and all this is going to be considered in a system of ultra-cold atoms, where such potentials can be created with the aid of the interference pictures of different number of standing laser waves applied to the corresponding system. Oh my God, I'm sorry. Since we are going to consider the atom's motion in such potentials, very important role will be played by the geometry of the accessibility regions for such atoms. This means that if the atom has an energy epsilon 0, then the accessibility region is given just by an equality 1. So it can move everywhere where its potential energy does not exceed epsilon 0. So the geometry of such regions will be very important, and it is very interesting for quasi-periodic potentials, and actually is rather non-trivial. As we will see, actually the quasi-periodic potentials can be divided into two classes. Let me just say that, move to, oh my goodness. Into two classes, since the quasi-periodic potentials are in a sense between the periodic potentials and chaotic potentials, we will see that actually it will be natural to divide all periodic, quasi-periodic potentials into two different classes. One class are represent some kind of regular potentials, and another class is closer to chaotic potentials. First of all, let me say that, of course, the geometry of the accessibility regions given by the inequality 1 is closely related to the geometry of level lines, because every accessibility region is restricted by some level line, and also it can be considered as a union of all the level lines with smaller energies. Yes. This problem is very interesting. I mean, the problem of describing the geometry of the level lines of quasi-periodic functions, and it was said by Novikov. And after that, it was studied very actively in his topological school. Actually, this problem is rather complicated, and its study depends on the number of quasi-periods of the quasi-periodic potential. So actually, even intuitively, it is understandable that if we consider the function with a function with 3 quasi-periods, that is the restriction of 3 periodic function on the plane, it is simpler than if we consider the restriction of 4 periodic function, 5 periodic function, and so on. Actually, 3 periodic potentials are very important also from another point of view. And actually, this problem was set by Novikov first in connection with another problem, the problem of electron transport in metals with complicated Fermi surfaces. And the first physical applications of the results obtained in this problem were in the theory of transport phenomena in normal metals. But here we are going to consider just the transport phenomena in two-dimensional systems, and our potentials will be just normal potentials in the coordinate space. Let me say now that as I already said, that we are going to divide the quasi-periodic potentials actually to two different classes, the class of regular potentials and class of chaotic potentials. It will be natural, and also it will be natural from the point of view of creating such potentials, to consider not just one potential, but some smooth family of such potentials, which depend in a smooth way on some finite number of parameters. For example, if we consider the potentials in systems of cold atoms, and we use the interference pictures of standing light waves, laser waves in such systems, we have a lot of free parameters when creating such potentials. For example, that can be amplitude of waves, directions of waves, periods of waves, maybe some phase shifts, and so on and so on and so on. So we usually have finite but big number of parameters which parameterize our potentials. So as we will see below, this parameter space, which is usually a smooth manifold or space, can be divided into two rather complicated sets. One set parameterizes regular potentials, and another set, which is a complement to the first set, parameterizes chaotic potentials. And the structures of these sets are, how to say, complementary to each other. So first set represents actually a union of infinitely many regions with piecewise smooth boundaries, and its complement the set which parameterizes chaotic potentials can be represented as a fractal in the parameter space. Okay, as I already said, it seems for us that the most convenient system for the experimental study of such potentials are systems of ultracold, two-dimensional systems of ultracold atoms. And what we are going to consider here are particle motions in such potentials, because they can be applicable to the study of transport phenomena in such systems. And using this study of transport phenomena, where we hope to study the geometry of such potentials, which can be created in such systems. Okay, usually quasiperiodic potentials which arise in system of cold atoms can be represented as a sum of finite number of sinusoidal harmonics. But still, from the point of view of geometry of the level lines, these potentials are general, and they have as complicated geometry as we want, like for any kind of quasi-periodic potential. So from this point of view, this is not a restriction at all for our problem. So I'm sorry. So let us now introduce this definition of regular and chaotic potentials, and we will start well, we will especially consider the case of 3 and 4 quasi-periods, because for these two particular cases, now there are serious analytical and topological results which describe the geometry of level lines of such potentials. And it can be said that no serious results for higher number of quasi-periods exist at the moment. So let us now consider quasi-periodic potentials, which are, for example, obtained by interference of 3 standing waves. Yes, this is a schematical picture. So we have a plane and we have 3 independent periodic pictures, 3 independent periodic potentials with different directions of lines, different periods, different amplitudes. And we want to describe the level lines, the geometry of the level lines of such potentials. First of all, we can say that if the energy is very low, then of course, if the energy is close to the minimal or maximum values of this potential, then level lines will be very simple. They will be like small circles which surround the corresponding energy values. But in between, in the intermediate values of energy, we can have something interesting. So let us make a remark that if we have a potential like written in the, here at the top of our page with 3 different cosines, independent cosines in the plane, then this function is, of course, a quasi-periodic function with 3 quasi-periods. We can easily construct the corresponding embedding, the embedding 3, and a 3-periodic function in 3-dimensional space, such that our function on the plane can be considered as a restriction of this 3-periodic function under the embedding number 3. Yes, so this is exactly the situation of quasi-periodic potentials with 3 quasi-periods. So let us make now give a definition. So we say that the potential has a regular open level lines if, first of all open level lines can be restricted by straight strips in the plane and pass through them from -infinity to +infinity. And this is not all. Actually, the direction of this line is connected with the directions of our one-dimensional potentials with the aid of some topological triple. Its direction is given by the by the relation 4, and here 2 integer numbers m1, m2, m3 arise, which are actually locally stable. It appears actually that this situation remains the same if we just change a little bit the parameters of our potentials, and the numbers m1, m2, m3 are the same in this situation. So let us give here some serious theorem which is obtained now for the potential with 3 quasi-periods. So let us now consider any potential with 3 quasi-periods and ask what is the geometry of its level lines. So first of all, we said already that for small or large values of energy, the geometry is simple. All the level lines are closed circles, but in between we have something different. So first of all, this is the general statement. For any such potential, open level lines, open means non-closed, level lines exist in some connected energy interval. This energy interval can have finite size or it can be just a point. So, oh my goodness. So Now, if this interval has a finite size, then all the open level lines of our potential are regular. And if this interval has zero length, this means that non-closed level lines exist just at one energy level, then they can be chaotic. So we can see that in the case of three quasi-periods, all quasi-periodic potentials can be naturally divided into two different classes. One class is closer to periodic potentials because its level lines are regular, and the second class is closer to chaotic potential. This is a typical level, well, schematically, this is a chaotic level line of such a potential, which exists only on one energy level. If we just change a little bit the energy, then it will disappear. It will be broken into closed level lines. So according to the conjecture of Novikov, for the case of three quasi-periods, the measure of parameters which give us chaotic potentials is zero, and also its Hausdorff codimension in the full set of parameters is strictly greater than 1. For example, here we show some example. This is the unit sphere, and it parameterizes the embeddings of two-dimensional planes into three-dimensional space. So if we just have an embedding of a two-dimensional plane into three-dimensional space, we can consider the orthogonal vector, a unit orthogonal vector, and the endpoints of such vectors, they give us a unit sphere, yes? And for every point on the unit sphere, we can ask which kind of potential we have for this embedding of two-dimensional plane in our three-dimensional space. In three-dimensional space, we consider just this very simple function, cosine xy plus cosine x2 plus cosine x3. So here, the green areas, they show us the stability zones. In every stability zone, we have regular potentials which have regular level lines. Every stability zone is characterized by its own set of integer numbers, m1, m2, m3. These integer numbers are different in these green zones. And so we can see that the complement to this union of infinitely many stability zones gives us some kind of fractal with some Hausdorff dimension, which is in this case is less than 2. Okay. Oh. Now let us say about some results for the case of potentials with 4 quasi-periods. Like in the full analogy with the previous case, the potentials with 4 quasi-periods are restrictions of 4 periodic functions under all possible embeddings of two-dimensional plane in 4-dimensional space. Also, we can say that for systems of cold atoms, these potentials usually have a finite number of harmonics, but it is not important for obtaining different geometries of their level lines. They are complicated enough. So let us consider, for example, let us formulate now the topological results for the potentials with 4 quasi-periods. Just for simplicity, let us consider the space of parameters, which is given like here by the amplitudes of the standing waves, their wave vectors, maybe phase shifts, and so on. So in this case, these results were obtained by Novikov and Dynnikov. We can formulate the following statements. So first of all, again, like in the previous case, we are interested in the geometry of open level lines of the potential, because the geometry of closed level lines is clear. So again, non-closed open level lines of potential always exist in some finite connected energy interval, or maybe at one point. Now we make the following statement. In the space of parameters, we have a set of open domains, and represents a unit of domains with piecewise smooth boundaries, such that in each domain we have the following thing. inside the domain, except the boundary.
Осталось меньше 5 минут. Прошу принять меры.
Interval. All the level lines again have a regular form. They lie in straight strips of finite width and pass through them from minus infinity to plus infinity, like in the previous case. And now for these level lines, we have the 4 tuples of topological numbers. So we have 4 tuples of integer numbers, which give us the directions, the mean directions of our level lines. So this means that again, in the for 4-dimensional case, we have the similar situation, because we have 2 rather complicated sets. One set is a union of infinitely many regions with different topological numbers, and its complement has a fractal type, and its complement corresponds to chaotic level lines. So there are 2 types of potentials. They exist on different sets parameter space, and one set is closer to regular potentials, the second set is closer to chaotic potentials. So let me just now say that when we pass to the potentials with a larger number of quasi-periods, that in this case, at the moment, there is no strong, rigorous, serious analytical results. But still, if we look experimentally at the families of such potentials, we can say that in principle, we have here similar situations. There are 2 sets. Okay. Okay.
Вы можете нас слышать?
I have some time or
no.
Okay. There is a similar situation. Let me just say that in this case we have two sets. One corresponds to topological numbers, and its complement corresponds to chaotic behavior of level lines. So now, what we are going to consider, what we would like to do, we would like to study the geometry of the level lines of our potentials using study of transport phenomena of non-interacting atoms in such potentials. So from this point of view, we can first say that the geometry of accessibility regions for atoms is very close to the geometry of level lines. For example, for a regular potential, we can see that the accessibility region for a quasi-periodic potential is regular, yes, and for chaotic potentials, the geometry of accessibility regions is also chaotic. And in this sense, we could expect the difference in transport phenomena in regular potentials and chaotic potentials. So first of all, in potentials of the first kind, we have to observe the strong anisotropy in transport phenomena for the corresponding energy levels. But this is true for many systems, like even interacting systems or even in heterodynamic regimes. But if we consider weakly interacting atoms, which means almost ideal gas in such potentials, that in this case, there is one essential moment which arises, because in this case, for 2-dimensional Hamiltonian systems, we can have a combination of integrability situation with the chaotic behavior of trajectories of particles. And usually how it appears on lower energy levels, we usually have mostly integrable situation, and on higher energy levels, we mostly have chaotic situation, diffusion situation. So what we expect that if we have an integrable situation, then the geometry of the accessibility regions does not affect much the transport phenomena. If we have the situation of the chaotic situation, if we have this diffusion situation, then the geometry of our accessibility regions can affect much the transport phenomena in our potential. So because of that, we numerically investigate here the dynamics of atom in different potentials, and what we are going to show is below. Yes, so say that we are going to consider again the restrictions of our very simple potential cosine x equals cosine x2 cosine x3 on two-dimensional plane and different affine embeddings, and we are going to consider the dynamics of our Is it okay? Okay. So so we are going to consider the dynamics of particles in such potentials for intermediate values. So first, let me show the first example. This is the example of a regular potential. So we can see that all the accessibility regions are regular, have regular geometry here. But if we consider dynamics of atoms in such regions, so we can see that in these regions, we can have different types of dynamics.